Hello, welcome to our lesson on geometric sequences and series. So in our previous few topics, we've talked about sequences in general, summation in general. We've had a focus also on arithmetic sequences and series. Today, the focus is on the same types of things, just geometric sequences and series. So what does it mean for a sequence or a series to be geometric? Well, remember that if we're talking about a sequence, we are just talking about an ordered list of outputs that is produced by a function, and we call our functions when they represent sequences a sub n instead of our typical function notation, and the inputs for that function are the natural numbers. Now again, if a sequence is what we're going to look at today geometric, it just means there's a specific pattern, and the pattern is what you might see in these first three examples. So I'm sure you can look at example 1 here and tell me what the pattern is to go from 3 to 6 and 6 to 12 and 12 to 24. We can see, hopefully, that we are just multiplying by 2 to get from one term to the next. So that is, unlike the arithmetic where we had a common difference, like the difference between these terms is 3, the difference here is 6, the difference here is 12. So there is not a common difference. Here there is what we call a common ratio. So instead of taking my second term and subtracting my first to find a common difference, if I take this term 6 and divide by the previous term 3, I get a common ratio of 2. And I would see that between any two consecutive terms. So 12 divided by 6 would be 2, or 24 divided by 12 would be 2. So instead of a common difference, we have a common ratio. So we would say this is a geometric sequence with a common ratio of 2. And here, instead of multiplying by a number, we are technically dividing what that's multiplying by a fraction, or the reciprocal of that number. So to get from, maybe it's easier to see, from 16 to 4, we would divide by 4, but that's going to be true all the way through. 256 divided by 4 is 64, 64 divided by 4 makes 16, and 16 divided by 4 makes 4. So here, our common ratio would be 1/4. If I am dividing by 4, the number I am multiplying by is 1/4, and again, you could take that 64 and divide it by 256 and see that 1/4 ratio. Now, arithmetic, I think, are a little easier to see the common difference each time because we're pretty accustomed to adding and subtracting. Sometimes it's not easy, though, to tell what our common ratio is. Like here, for instance, especially because they're decimal form, I can't tell what I'm multiplying by or dividing by to go from 0.42 to 0.294 to 0.2058. So the only way to find a common ratio, well, for me at least in this case, would be to take my two consecutive terms and divide them. So my common ratio in any case, but in this case is super helpful, would be the ratio, again, of two consecutive terms, starting with a later term. So 0.294 in this case divided by 0.42 is going to show me, let's see, divided by 0.42, then I have 0.7 as my common ratio. And just to double check that, what I'm saying is if I multiply by 0.7, I should be able to get from one term to the next on this list. So obviously 0.42 times 0.7 gets me to 0.294. If I multiply by 0.7 again, I get to 0.2058, so we are good. There's our common ratio. Okay, so if a sequence is geometric, again, there's going to be a common ratio between the terms, and we will define that common ratio as, again, a ratio, a fraction, a quotient of any two consecutive terms, but the next term divided by the one previous. So we're going to say a sub n plus 1 divided by a sub n. Now sometimes we say previous term as a sub n minus 1, but if I defined it this way, and our smallest natural number input being a 1 means when I input a 1 in the denominator here, 1 minus 1 would be 0, and a sub 0 is not defined for a sequence, and so we're going to go the other direction with this and just say a sub n plus 1 over a sub n. But in general, take your two consecutive terms and divide. As long as it's the next one divided by that previous one, you'll get your common ratio. Okay? Now to connect to some prior learning. Let's say our geometric sequence is 4, and then 8, and then 16, and then 32, where we are multiplying by 2. So we have this geometric sequence with a common ratio of 2. Remember, what it means is there is a function, some function a sub n, where when I input natural numbers, these are my outputs. So when I input a 1, my output's a 4. And when I input a 2, my output is an 8. When I input a 3, it's the third number on the list. When I input a 4, it's the fourth number on the list, right? So if I graphed this as a function, then at 1, 4, I have a point. So this is going to be like here-ish. And then at 2, 8, I tried to spread the graph out a little bit. I'm going to have a point, so like up here. And then at 3, we're going to jump up to 16. So that would be like here-ish. And then at 4, we're going to jump up to 32. And that's going to be like around here. And what we would see, again, not a connection of these points, but if we are continually doubling our outputs, we're going to start to see this thing take off and grow really quickly, which is exactly the behavior we see in an exponential function, with a growth factor of 2 from one output to the next. So if I wanted to actually write the explicit formula for this sequence, it would be the same thing that I would do if I was writing an equation for an exponential function, and particularly when it's in context. So remember, when we're writing an exponential function in context, we would say y equals a times b to the x power. And just to refresh your memory, if I was graphing, let me get rid of all this. Let's just say y equals 2 to the x power. Then we know what exponential functions, right? What our exponential growth looks like. So here's the concept. In context, we would, just focus on the first quadrant, and that's pretty similar to what we're doing here. But in context, we would start on the y-axis at 1, and then we would grow from there. And we know that if we made this number in front here something other than 1, like right now it's a 1, it crosses at 1, if I change this number out here to a 4, then remember, anything to the power of 0 is 1. So if I raise 2 to the 0, I get 1, but now I'm multiplying by 4, so I see it cross the y-axis at 4. Or if I change this to a 10, now it's going to cross up here at 10. So that would be the starting point on the y-axis, and then b is our growth factor, okay? Now in this case, we're not starting at an input of 0, we're starting at an input of 1. So I want the same concept. Where does my situation start? That's A. And what is the growth factor? What am I multiplying by to continue my list? In this case, that's going to be R. Now, because I'm not starting at an x value of 0, I'm starting at an x value of 1, I'm going to shift over 1 by subtracting 1 from my input. So that is how I am able to, or that is the connection to be able to write an explicit formula for this exponential situation. So in context, an exponential function would just be y equals a times b to the x. With a geometric sequence, we know that we're going to replace y with a sub n. The starting point here is going to be the starting point here. It's going to be the starting output here. In this case, it's going to be 4. So this will just be a sub 1, the first number. B is our growth factor, but in this case we're calling it R. That's the number we multiply by to go from one number to the next. And then we are going to raise this to the nth power instead of the x power. But because we're starting at the first, or an output of 1 and not an output of, an input of 1 and not an input of 0, we're going to shift over and call this an n minus 1. So in place of x, n minus 1. So for this particular situation, we would say a sub n is equal to, well, we're starting at an output of 4, and then we're multiplying by 2 to the n minus 1 power. And that would be an explicit formula for this particular geometric sequence. But in general, we can use this to write an explicit formula for any geometric sequence. So remember, what the explicit formula does is it helps us calculate any term that is on the list, so any term in the sequence. So if I ask you to find the 5th term here, I don't need a formula for that. I can just take the 32 and double it. But if I wanted to know the 15th term, I don't necessarily want to have to double that many times, so I can just plug 15 into my explicit formula and find that term. So we're going to say the explicit formula is going to be a sub n equal to a sub 1, that's where my list starts, times b, that's not b, b is what we use in an exponential, times r, that's what we multiply by to continue our list, and then we're going to raise it to the n minus 1 power. And the minus 1 because we're starting at 1 instead of starting at 0. Okay? So let's just practice writing the explicit formula for example 4 here. So we're going to say a sub n is equal to, this list starts at -6, and I can see here I am multiplying by 3 to continue this list. And if you weren't sure, remember you could always take the second term and divide it by the first term, and there's your 3 for your common ratio. So 3 in the parentheses, and then raise it to the n minus 1 power. So that's your explicit formula. Now remember, the purpose is to calculate a term, so we would do the same thing in number 5. If I want to find the 15th term, I'm going to start by writing my explicit formula. So I can see here I am multiplying by 4, and that's going to continually grow there. Or again, if you took 32 and divide it by 8, you would see that common ratio of 4. So any term here, okay, is going to be, let's see, this list starts at 8, and then we multiply by 4 to the n minus 1 power. Now, if I want to find the 15th term, I also input the 15 for n. So a sub 15 would be 8 times 4 to the 15 minus 1 power, or the 14th power, which is what I would type into the calculator. So 8 times 4 to the 14th gives me a really large number. So that is scientific notation if you've not seen your calculator produce that kind of an output before. 2.1, I don't know why it does this, to be honest, because it gives you so much of the decimal. 648 times 10 to the 9th power means I gotta move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 places to get the number in standard form. So like, I don't know why it puts all those digits there and then says multiply by 10 to the 9th instead of just giving me the number without the scientific notation of the decimal. It's kind of silly, but that's all it means. If this had been a negative exponent, then I would have moved the decimal to the left. Because it's positive, I move the decimal to the right, the number of places that power indicates. So 2147483648. So put some commas in so I could read this. We're looking at our 15th term being 2,147,483,648, and that was the 15th term again. So let me just go ahead and put that notation in there, and there you have it. So although I could continue to multiply by 4 to make this list and get out to the 15th term, doesn't seem like it would be overly difficult, but the numbers grow so fast then that the list would start getting a little ridiculous. Okay, so you could absolutely take the long way and multiply by 4 to continue the list, but there you go, that gigantic number. Alright, so look, I want you to give the next one a try. If you are feeling good about this, pause the video and give it a shot. If not, let's see. Let's write our explicit formula so we know a sub n. Here is going to be, let's see, a sub 1 they give us directly, negative 4,096. That's where this list starts. And then it says the common ratio is going to be a 0.25, and then we're going to raise that to the n minus 1 power. Now this one, telling us to find, let me change colors here, the 12th term, so a sub 12, would be negative 4,096 times 0.25 to the 12 minus 1 power. And again, I'm just going to go into the calculator with this one. Now this time, notice the common ratio being like a growth factor, right? Some fraction or decimal between 0 and 1 means we would be looking at a decaying situation instead of a growth situation. So I know I should have a number that's much smaller than 4,096 instead of a number that was much bigger like we saw in the last example. So negative 4,096 multiplied by 0.25 to the 12 minus 1 would be 11th power, and there you have it. Now that decimal is not difficult to write down, but in the blue, if we can change this to a fraction that's a little bit cleaner, then I probably would write this in fraction format, and yeah, that looks a little nicer to me. So the decimal would be fine, but I'm going to call this negative 1 over 1,024, and that would be the 12th term on this list. Negative 1 over 1,024. And there we have it, okay? So arithmetic sequences that we looked at in the previous topic, we saw those with linear behavior. These are exponentially behaving here. And these are our explicit formulas where we can find any term on the list. Hopefully we can also find the common ratio if we needed to. But remember, we can also define our sequences recursively. So when we're defining a sequence recursively, that means we are defining it with respect to previous terms. So when we do this, we have to state the first term, at least, like where does the list start, and then in this case we need to know what are we multiplying by to continue that list. So we're going to plug r into a formula that says any term in general on our list is going to be r times the previous term, so a sub n minus 1. And again, this will be for n's that are greater than 1 because we're going to be stating what that first term is. So we know the first term, and then any term after that would be r times the previous term. So for instance here, to get from negative 5 to 15, I'm multiplying by a negative 3. So we would say, okay, first, this list starts at negative 5, and then any other term on this list would be negative 3 times the previous term. And that's it. Defined recursively by stating the first term, and basically what is the pattern? The pattern here, we're multiplying by negative 3 to continue this list. Okay, so we should be able to do that whether we're given the actual list or given the information about what produces that list. So if we're given the explicit formula, have to recognize that this is where the list starts and this is what we multiply by to continue that list. So I know that this represents a sub 1 and I know that this represents r. So I would say, again, a sub 1 is 2, and then in general any term on this list would be 1/2 times the previous term. And done. We're defined recursively. Oh, and I should state here for n greater than 1. And I forgot that piece over here. This would be for n greater than 1 because 1 was already defined. And if I didn't say that, then again, inputting a 1 here would make a sub 0, which isn't defined. So I have to make sure I state that. All right, we got the last piece. So we understand what a geometric sequence is. We know how to define it recursively and explicitly. Now, let's talk about the sum. If we're finding the sum for a geometric series, we're just adding up the terms of the geometric sequence. So a geometric series, again, just representing a sum. And I've got a couple of formulas here for you, both written with the sigma notation in addition to a formula, but really the formula is going to be what we're going to use to evaluate. So you could see a geometric series written with the sigma notation just to condense the question, I suppose, but we have to be able to use this formula to evaluate. So we don't have any nice properties to be able to cut this up in the same way we did with the linear, or that we could with like a quadratic or a cubic or something that's polynomial based, exponential being a little different. So we're going to stick to this formula. If we are looking for the sum for a finite geometric series, that means we're starting at the natural number 1 and going to the nth term. And we have, so we know those number of terms. We also have to know our explicit formula. But if that's what we're doing, okay, finding a finite geometric series that starts at n equals 1 and goes to n, the sum for those n terms will be a sub 1 multiplied by this fraction, which is 1 minus r over n, r to the nth over 1 minus r. So in order to use this formula or evaluate the sum for a finite geometric series, I need 3 things. I need the first term, I need the common ratio, because that's 2 spots here, and I need to know the number of terms. Now, whether that's given to me in sigma notation or not, this is the formula I have to use to evaluate. Now, there's a stipulation that r can't be 1, because we're not looking at a growth situation in that case, so we're not going to see r be 1, but that is a stipulation of this formula. Okay, also, not just because if we had a common ratio of 1, we wouldn't be looking at a growth situation, but in this formula, plugging in a 1 for r would make a fraction that's undefined. Okay. Now, if we have a not a finite but an infinite geometric series, we can still evaluate if that series is convergent. So what does it mean for it to be convergent? We talked about this before. It means that the values approach, or that the outputs are approaching a specific real number value, and that's going to happen in a decay situation. So I'm just going to put a decay function in here. Like when we see y equals 2 to the x power, that's a growth situation. That's not going to be approaching a real number value as the inputs are increasing. But if I make this instead of 2, if it becomes 1 over 2, or any fraction or decimal that's between 0 and 1, then again we're going to say or see the decaying situation. So in this case, our values are getting closer and closer to 0. That's where our asymptote would be. So if we're looking at a sum, just kind of think about what's happening here. Okay, let's say that this is in fact the sequence that we were looking at. So we start at 1 and then we cut that number in half. But now I'm trying to add these terms together, okay? So I have a 1 and then I'm going to add a half the next term, and then if I cut that in half I would have a fourth, so I'm going to add that on here. 1 divided by 4, and then half, I said 4 and I typed in a 1. I got fat finger problems. Okay, so 1/4 times a half would be 1/8. I'm going to add that next term. And then 1/2 of that would be 1/16. Let me add on a 16th. And then let me add on 1 over 32. And let me add on 1 over 64. And what's going to happen, and you're going to see it, I'm going to continually add fractions that we said are converging to 0, right? If my fractions that I'm adding on here are becoming infinitely small, then I'm continually adding something that is approaching 0. If it's a fractional value that's getting closer and closer to 0, it's going to have an insignificantly small impact on my sum. So not only will the outputs converge, but the sum of the outputs will converge. So we can actually evaluate or find the value of a sum of an infinite list of numbers, but that infinite list of numbers has to be convergent, okay? Those fraction values got to be getting smaller and smaller, so that when we add them, they are not affecting the sum. If we have something that grows infinitely, then the sum would be constantly growing infinitely as well. It would not be possible to evaluate that sum. But if the list is converging, when I add the list, it will also converge. So we have a formula. It's again, if we're finding the sum for an infinite number of terms, we're going from 1 to infinity here. And again, we have our explicit formula. This is the formula we will use to evaluate. So I need to know the first term and the common ratio. As long as that common ratio is less than 1, and we'll say the absolute value of the ratio is less than 1. So whether we're multiplying by a positive or a negative, if we see the values converge, so we have something between 0 and 1, positive or negative for our ratio, that's going to happen, okay? So we've got all this notation in here, but basically two formulas. If it's finite, this is our formula. If it's infinite and convergent, this is our formula, okay? So let's try this out. This says to find the sum from the first term to the fourth term of a sequence that is produced by this explicit formula. Now, I'm not going to lie to you here. I have a formula, right? I just boxed it in up here to do this. I would probably not use a formula here because I'm adding up 4 terms, and it would be really easy for me to just list those 4 terms and add them. And this formula, not always the easiest, right? I got fractions in there. Okay, so I'm going to just expand this one out. I already know the first term on my list is going to be 9, and then I'm multiplying by 3 to continue this list. So my next number would be 27. 27 times 3 is 81, and 81 times 3 is 243. So without even a calculator, I know the 4 numbers that I'm trying to add, and now I can just add them. So 9 plus 27 plus 81 plus 243 means my sum is 360. So I did not need anything fancy for that, and if that's the case for you, then you don't use a formula. So here is the sum for those 4 terms, 360. Okay. Now also remember, you have sigma notation in your calculator, not for your quiz, but while you're working, if you want to verify what you're doing, going from the first to fourth terms, and we've got 9 times 3 to the n. I need an n to make this match. Minus, whoops, I gotta make sure my -1 stays up here in the exponent, so I'm gonna put it in parentheses. I don't know if you noticed, let me just do that again. If I don't put parentheses and I just type a -1, the minus is no longer in the exponent. So we have to make sure to keep that -1 with n if we want to confirm our work in there. We get the 360, okay? So we have this formula, but again, if I'm adding 4 terms, 3 terms, some small number of terms, I'm probably not going to use a formula. And it is nice that if you weren't sure about the formula, you always have this default way, the long way about finding a sum. Alright, so similar process here. This is a geometric series, and it tells me it's geometric, so I'm going to be multiplying by 5 to move along this list. So I know my common ratio, I know my first term, but in this case I don't know my number of terms, so I'm just going to expand this list out because I don't think it's going to take too long to get to 625, being that exponentials grow really quickly. So I have 1, 5, and then 5 times 5 would be 25. 25 times 5 would be 125, and 125 times 5 is 625, so there it is again. I don't need any fanciness for this. I already have all the numbers on my list. Now I can just add them together. And actually, I don't think I need a calculator. 6, 750, 775, 780, 1. But my lack of confidence will have me go to the calculator anyway. And 625, and there it is, 781. So here we have the sum for 1, 2, 3, 4, 5 terms, amounting to 781. Okay, so if a formula is avoidable, then don't use a formula. But looking at number 9, I'm trying to find the sum for 12 terms. I don't want to list those 12 terms out and then add them together. So I would have to create the list by multiplying by -4. Those numbers are going to get really big really fast. Multiplying by 2.5, they're going to get big. And then after I find all the numbers, add them. I don't want to do that work. I think a formula would be easier in this case. So the formula says that the sum for, in this case, 12 terms is going to be a sub 1 multiplied by a fraction. In the numerator of the fraction, it's 1 minus r to the nth power. So 1 minus 2.5 to the 12th power. And on the bottom, 1 minus r, so 1 minus 2.5. And then we go to the calculator. So let's see. -4, parentheses, fraction, 1 minus 2.5 to the 12th power. 1 minus 2.5, and that, is there a decimal in there? Yeah, my eyes are not so good. I'm going to see the fraction, see if it looks any better. Yeah, I don't know. I don't know which one of these looks any better or worse, or that either one looks better or worse, so you can just choose, pick your poison. I'm going to go with the decimal this time. -1589. 158,943.05273.4. Now, because that is an exact, precise decimal that stops, I probably wouldn't round it. If you like the fraction better, choose the fraction, but there it is. That would be the sum for those 12 numbers on that list. Okay, so sum is boom. And alright, so look at the next one. Again, we're evaluating a geometric series. It's 10 terms, it's finite, so I know I'm using that first formula again. Although if you wanted to, you could make your list of 10 terms and add them. I would not choose to do that for 10 terms. So again, we'll say the sum for our 10 terms is going to be our first term, that's given to me as 2. And then it's 1 minus the common ratio to the nth power on the top of the fraction, and then 1 minus the common ratio on the bottom. And now, I was a little sloppy here, but sort of on purpose to talk through this with you. On the last one, so the formula has a negative in it. When I raise 2.5 to the power of 12, that negative is going to be intact. The power applies to the 2.5, and then it gets multiplied by the negative as it should. So I don't have any issue here not using parentheses, although technically we should have put this in parentheses. Now that's going to be more important when our common ratio is negative. If I don't put the parentheses here, I don't know that the calculator is going to do this correctly. If the parentheses aren't here, the 10 is going to apply to the 3, and then it would multiply by a negative, and then it would multiply by another negative. And that's going to give us a positive result, which is not what we want here, because we want -3 to be raised to the 10th power, and then we want it to be multiplied by a negative. So it's good practice to use parentheses when we input values into formulas. So again, I did this a little sloppy, just sort of on purpose to bring this up as a talking point. But if you know what your sign's going to end up being, then don't worry about it. But use those parentheses if you want to be sure that the calculator, or you're telling the calculator to do the appropriate thing. So here, and you'll see, I'll show you in the calculator how you're going to get different results if you don't put those parentheses. So let me just recycle. Got 2, and this should be, oh, it took away my exponent. -3 to the 10th power, and then minus a 3 here, and that's 29,525, whereas if we put the parentheses around it to make sure that the 10 applies to the negative 3, we get a negative answer instead of a positive. So that's a big difference in the result, okay? So those parentheses are important. Not so much on the bottom where we don't have an exponent, because the negative does what it should there. But to be safe, if you don't have to or want to wonder, and guess, and when should I use parentheses, when should just use parentheses when you input numbers into formulas, okay? So this is going to be negative 29,524 for our sum. And it should make sense the sum is negative, not positive. Think about it starts at 2, and then we're going to multiply by a negative. So positive times a negative is going to be a negative. And, well, maybe not. I guess you could argue. Yeah, okay, so think about if you're making your list. You're at 2, and then you're at negative 6, but then you multiply by a negative again, so you get 18, and then you multiply by a negative again. So the signs are going to alternate. Maybe it's not particularly easy to tell if that's going to be negative or positive, but bottom line, use parentheses and you'll be safe. Okay, let's look at the next one. So a little detail here, right? This is an infinite series that we're trying to evaluate. We can only evaluate an infinite series if it is convergent. And it's going to be convergent when we have a decaying situation, which is what we have here. So that ratio needs to be, the absolute value of that ratio has to be between, well, if it's absolute value, it's going to stay positive. So it's got to be less than 1, basically. But we're looking at a decay situation, so I know that I can evaluate this. So this sum for this infinite number of terms, the formula is a simple one. On the top is the first term, that's given to me here is 10, and on the bottom it's 1 minus that common ratio. And really shouldn't have to go to the calculator for this. 5/5 minus 1/5 is 4/5, so that would be 50/4, or 25 halves, or 12.5, but let's just be safe. 1 minus the 1/5, and look, I did it again. Let's use parentheses to be proper. So 12.5, there it is. Or if you like the fraction better, that would be 25 halves. So I'm going to go with 12.5, but you can make the fraction if you like that better. There it is. Okay, look in here. Again, this little dot, dot, dot is telling me that this is an infinite sum that I'm trying to evaluate. But in order to do this, it has to be convergent. Now, I'm looking at these values. They are not converging. If I keep multiplying by 3, which is what's happening here, those numbers will just get larger and larger and larger. So since that common ratio is bigger than 1, this is a growth situation. It's not going to be convergent, which means this is not possible to evaluate. So the sum is, it's not possible. This isn't, I'm not sure what's the word. You can't evaluate this. It's I don't know, we wouldn't say the sum is undefined. It's eventually, it's whatever. Not possible to evaluate. I'm playing semantics in my head, just don't mind me. Okay, because this is not convergent. And by the way, if it's not convergent, that means it's divergent. Maybe I should use that word. Not convergent, it is divergent. It needs to be convergent in order to evaluate if it's an infinite sum. Okay, the last one, again, one for you to try, is going to be one that actually does converge. These values getting smaller here, I can tell I am multiplying by 2/3, and then if I multiply by 2/3 again, this list will continue. So since this is convergent, because the absolute value of 2/3 is less than 1, this is going to be a decaying situation or a convergent situation. So I can evaluate the sum using the same formula that we looked at in number 11 there. So the sum for the infinite number of terms is going to be first term on the top, which is 1, and then 1 minus the common ratio of 2/3 in the denominator. So 1 minus 2/3, that'd be 3/3 minus 2/3, that's 1/3, and there are 3/3 in 1, so we don't need a calculator for this, but if you want to see it, because you don't believe what I just talked out there. 1 minus a third in the denominator, and what did I say? Oh, 2/3. I'm like, what the heck? I mean, I'm like, I make mistakes, but man, I was going to feel real bad about that one. Okay, so this would be 3, like I said. So the sum for the infinite number of terms here. When we say that the sum for the infinite number of terms on this list is 3, it's not that's not really the proper way to say it. So what we would say is the sum for this infinite number of terms is approaching 3. So if you continually added these fractions that were 2/3 what they were, right? These fractions get smaller and smaller and smaller because this thing converges. Again, the fractions that we add on have less and less of an impact. What we would see is our sum getting closer and closer and closer to 3. So we'll never actually get there, but we would approach that value. So just like the fractions never get to 0, this sum will never get to 3. We would say it approaches 3 or converges to 3. Okay, so the actual sequence, the outputs converge to 0, but the sum of the sequence, the series, approaches 3 or converges to 3. Okay, so hopefully the language makes sense there, and hopefully you've got enough formulas to get going on your practice. But as always, if you need some extra help, then just reach out. Until next time, take care.